Hey everybody, just wanted to take a minute and talk about some nuclear reactions. Now that we kind of have an idea of what nuclear decay, natural nuclear decay looks like, there's reactions that occur, okay? And we can maybe understand a little bit of this when we talk about the types of decay that there are, or the types of radioactive reactions there would be. So there's usually emission reactions, and there is then capture reactions, okay? And so emission reactions, the word emission, as I go through all of these, sorry, the word emission, okay, emit, okay, emission, emit, means that you're going to find these things as a product, okay? In most of the nuclear reactions that we have, that we're going to be studying, are emission reactions, okay? There's only one that's really that I can think of that is going to be a capture. There are a lot of capture reactions, but there's going to be just one I think that we're going to be talking about. But this one's later on down the line. Okay, but nonetheless, let's get rid of this. And let's take a look at what we do in order when we see reaction. So here we have Pu, okay, plutonium. Plutonium is naturally radioactive. And what happens is plutonium here gives off an alpha particle, okay? Keep in mind this is an alpha particle here, okay? You'll see it written both ways. I'm just kind of covering it up here because I prefer this, because this tells me we're dealing with a helium nucleus. If I put the alpha sign here, that tells me that we're dealing with radioactive decay, okay? And so when we do a single step reaction like this, all we have to do, let me erase this because it's going to get in my way, okay? All we have to do is balance this, and yeah, it's all balanced, but we want to make sure that the charge and the mass is balanced. And so here we have a mass number of 2. So in order to get that right, that's going to be 92, because 92 plus 2 is 94. And we do the same thing here. 4 plus what? This side has to equal this value over here. So that's 238. And then we look up on a periodic table and we find that uranium is element number 92. Okay, and we do the same thing here. Here's beta decay. Sorry, I was going to say electron capture or something. I don't know, but it's beta decay. And when we have beta decay, okay, we do the same thing. This is going to be 32. The mass isn't going to change. 32 plus 0, and then 16. This is where it gets tricky. I'll say tricky because, you know, this is the part where people have a tendency to have an error. There's 16 plus a negative 1. So 16 plus a negative 1 is 15. Okay, so just keep that in mind, that that negative is there. When you look on a periodic table, element number 15 is phosphorus. Okay, so these are what single step equations look like, and we have to keep in mind that we use the correct radiation type when we do this. Okay, there is an interesting side note which I wanted to point out, and I still remember my own chemistry teacher in high school telling me this, is that we have a neutron which has a mass of 1 and no and no atomic number, because okay, and when this breaks down to form an electron, which has no mass and a negative 1, and that gives us a proton, which has a mass of 1 and a positive 1. Okay, and I always found that interesting, that a neutron equals an electron plus a proton. For some reason, that always just struck me as something that was totally interesting, that nature has, is that the neutron is kind of equal. It's not exactly equal because there is a difference in mass, but I still think that that's, to me, I don't know, it just always stuck with me. So I'm trying to pass that along to all y'all out there, is that, there is a certain beauty and pattern in chemistry that that nature provides us. So, okay, well that is kind of the introductory thing about nuclear reactions, and have a great time.